Let's take a look at the current state of space. Turning away from the Sun, planets, asteroids, and comets, humanity gazes into the boundless depths of deep space. It seems as if nothing separates us from the infinite starry distances. Yet a question arises. Is interstellar space truly empty? Or are there invisible barriers separating us from those distant suns? The outer solar system. Contrary to popular belief, the region beyond Neptune is far from a perfect vacuum. As previously noted, comets fall into two main categories. The first type has orbital periods of less than 200 years, and generally orbits the Sun in the same direction as the planets. The second type has much longer orbital periods, with trajectories that appear chaotic and scattered in all directions. This presents a puzzle. Comets lose material each time they approach the Sun. Logically, over millions of years, they should have completely evaporated. Yet 4.56 billion years after the solar system's formation, comets continue to grace our skies. Where do they come from? To find answers, we must travel back in time, roughly 4.5 billion years, to the nascent solar system, born from swirling, flattened disks of gas and dust encircling the young Sun. The inner planets, closer to the Sun, were warmer and smaller, composed mostly of rock. The outer planets formed in colder regions and grew far larger. In the coldest reaches, water existed as ice mixed with dust and other compounds. Tiny icy fragments collided, merged, and gradually grew, some reaching hundreds of kilometers across. But a problem emerged. The massive outer planets exerted immense gravitational pull. Icy bodies drifting too close were either absorbed into the planets or flung onto radically different orbits. Some hurled sunward, others ejected into the void of deep space. The giant planets scattered trillions upon trillions of these icy spheres. Though tiny compared to planets, these objects had low mass and weak gravity. Thus, while a planet strongly pulled on them, their pull on the planet was negligible. Yet over trillions of interactions, their cumulative effect became significant. This process is described by the modern Nice model, named after the French city where it was developed. It shows that these repeated gravitational encounters caused Saturn, Uranus, and Neptune to slowly migrate outward, while Jupiter moved slightly inward. Neptune had the strongest influence because it bordered the region where most icy bodies resided. As Neptune migrated outward, close encounters flung these objects onto highly elliptical, tilted, and eccentric orbits. Distant, repeated interactions gradually stretched their paths even farther. This dynamical reshuffling is thought to have triggered the Late Heavy Bombardment, a period hundreds of millions of years after planetary formation, when a flood of outer solar system debris cratered the surfaces of planets and moons. While not definitively proven, the match between this hypothesis and observed cratering patterns is compelling. Today, we recognize three distinct reservoirs of these icy bodies. The first is a disk-like region, shaped like a donut, lying parallel to the planetary plane. Objects here have stable orbits, largely undisturbed by Neptune. This is the Kuiper Belt, named after Dutch astronomer Gerard Kuiper, who first predicted its existence. It begins just beyond Neptune's orbit and extends from about 4.5 to 7.5 billion kilometers from the Sun. The second region is the scattered disk, formed from icy bodies Neptune flung onto strange, highly elongated orbits. It overlaps with the inner edge of the Kuiper Belt and stretches out to roughly 150 billion kilometers, about 25 times farther than Neptune. Beyond both lies a vast spherical shell of icy objects located around 300 billion kilometers from the Sun, roughly 70 times Neptune's distance and an astonishing 2,000 times farther than Earth. This is just its inner edge. It may extend as far as 1 light-year, about 10 trillion kilometers. Known as the Oort Cloud, after astronomer Jan Oort, who first proposed it, this distant realm is the source of long-period comets. Their highly elongated, nearly parabolic orbits bring them into the inner solar system from random directions in the sky. Many recently discovered comets belong to this group. In contrast, the scattered disk supplies short-period comets. Neptune's gravity can perturb their orbits, sending them inward toward the realm between Jupiter and Neptune. Subsequent encounters with Jupiter may then nudge them even closer to the Sun, transforming them into the short-period comets we observe. So how do comets form? For much of history, this, and much else about deep space, remained speculative. Until 1930, when American astronomer Clyde Tombaugh made a pivotal discovery: Pluto, the first known Kuiper Belt object. Pluto follows a highly elliptical and inclined orbit, bringing it closer to the Sun than Neptune at times. This raises a natural question: why don't they collide? The answer lies in their orbital dynamics. Although their paths cross, Pluto's orbit is tilted significantly above the solar system's plane when it reaches perihelion, its closest point to the Sun, keeping it safely away from Neptune. Moreover, Pluto orbits the Sun twice for every 3 orbits Neptune completes. Thus, when Pluto is nearest the Sun, Neptune is always about 90 degrees away, billions of kilometers distant, minimizing gravitational influence. This 3-2 orbital resonance is likely not accidental. It probably resulted from gravitational interactions and friction during the early solar system's chaotic phase. Billions of years ago, Pluto's neighborhood teemed with objects on varied trajectories. Those that ventured too close to Neptune were either ejected, turned into comets, or absorbed. Only objects locked in stable resonances, like the 3-2 or 2-1 with Neptune, survived. Today, these resonant bodies, called plutinos, dominate the region near Neptune. They're not a distinct class, but a special subgroup of Kuiper Belt objects, KBOs. After Pluto's discovery, astronomers wondered if it heralded a new population of icy bodies beyond Neptune. For 6 decades, the search continued. In 1992, the object 1992 QB1 was found, ushering in a new era of Kuiper Belt discoveries. Today, over 1,000 KBOs are known. Among them is Eris, nearly Pluto's size, but more massive, possibly because it's rockier than icy Pluto. Pluto itself is fascinating. In 1978, its large moon Charon was discovered. Charon is so massive, about 1/8 of Pluto's mass, that the two bodies orbit a common center of gravity located in the space between them. 4 smaller moons were later spotted in Hubble images, 2005 and 2012, and more may exist. Pluto is small and distant, so our knowledge remains limited, though that was about to change. At the time of this writing, NASA's New Horizons spacecraft is en route to Pluto, scheduled for a historic flyby in July 2015. Undoubtedly, our understanding of Pluto will transform. New moons may be found. Surface features will be revealed for the first time. But since those data aren't yet available, perhaps the best we can do is leave little Pluto in peace for now. Still, one point is worth making. Pluto was discovered in 1930, long before any other Kuiper Belt object, because it's unusually bright. Initially thought to be Earth-sized, later observations revealed it's smaller than Earth, the Moon. Its surface is highly reflective, making it appear brighter than it truly is. Most KBOs are darker and far dimmer. If Pluto is the king of the Kuiper Belt, it has countless subjects. We estimate the belt contains around 100,000 objects, wider than 100 kilometers. But that's dwarfed by the Oort Cloud, which may hold trillions of icy bodies, though none have been directly observed. 2 intriguing outliers, Sedna and 2012 VP 1113, add further mystery. Sedna orbits at about 140 billion kilometers from the Sun. VP 1113 is roughly half that distance. Both have highly elliptical paths that never approach Neptune. How they got there is unknown. Perhaps they're inner Oort Cloud objects, nudged inward by passing stars long ago. But no one knows for sure. Here's another puzzle. Models of solar system formation suggest the Oort Cloud should contain about 6 billion cometary nuclei. Yet estimates based on observed long-period comets imply 400 billion objects. That's a staggering discrepancy. The only plausible explanation? The Sun may have stolen comets from other stars. Since comets form wherever stars do, and young stars often pass close to one another, it's possible that some of the long-period comets we see originated in alien star systems. Could the dazzling comet in our sky be an interstellar visitor? It's entirely possible. There's also a more dramatic hypothesis stirring scientific imagination. A hidden planet may lurk far beyond Neptune. Preliminary studies reveal a curious alignment in the orbits of some distant KBOs and long-period comets, as if shaped by the gravity of a massive, distant world. NASA's WISE telescope scanned the sky in infrared and ruled out a Saturn or Jupiter-sized planet out to vast distances. So if this Planet 9 exists, it must be smaller, perhaps Earth to Neptune sized, and orbit tens of billions of kilometers away. We know exoplanets exist at such distances around other stars, so the scenario is physically plausible. But does it exist? For now, the answer remains uncertain. This remote frontier of our solar system remains largely unexplored. not just because of its distance, but because of its sheer emptiness. In such vastness, an entire planet could hide undetected for centuries. The key takeaway? Our solar system still holds profound secrets. The exploration of these dark, icy realms has only just begun. In summary, beyond Neptune lie vast reservoirs of icy bodies capable of becoming comets if perturbed inward. The Kuiper Belt is a donut-shaped disk aligned with the planetary plane. The scattered disk, more eccentric, feeds short-period comets, and the distant spherical Oort Cloud supplies long-period comets. These objects likely formed near the giant planets and were later scattered outward by gravitational interactions. This episode of Crash Course Astronomy was produced in collaboration with PBS Digital Studios. Be sure to subscribe to their channel for more incredible content. Written by Phil Plait. Edited by Blake DiPastino. With scientific consulting by Dr. Michelle Thaler. Directed by Nicholas Jenkins. Script supervision and editing by Nicole Sweeney. Sound design by Michael Aranda. And graphics by Thought Cafe.